So real-time RAG, it's just like RAG, but for data that keeps changing.
That's right, Greg. And also, what data doesn't keep changing?
Oh, yes. Got 'em. Yeah. So are there any use cases that we should keep in mind that this sort of approach is particularly good for?
Real-time analytics is really good for data that comes from IoT devices and any data that keeps changing in real time. This includes things like news. Every single day we have new streams of news coming in, anything to do with financial markets and pricing.
Very cool. How about building these things? The infrastructure, is it way more challenging? Is there significant difficulty associated with adding the real time into the RAG?
Well, that's what I'm very excited to share with you today. We can build these pipelines by using Python and our favorite Python packages through a concept known as the data flow.
Nice. All right. That sounds dope. I can't wait. We'll have you back in just a second. Welcome, everybody. My name is Dr. Greg, and that, my friends, was Laura, aka Laura the Legend. I'm the co-founder of AI Makerspace, and today we've got a special event for you. Laura is actually one of the very best community members we've ever had. And since she builds, ships, and shares like an absolute legend, we wanted to bring her expertise to you guys because she is great at presenting both concepts and code, similar to how you're used to seeing from me and the Wiz. A little bit more about Laura Gutierrez Funderburk, aka Laura the Legend. She's been in the community for a while, and back when she was getting started, she was coming out of a background of mathematics. She became interested in coding and community building. She went to work as a DevOps engineer and then a data scientist in 2019, and ultimately got into developer advocacy in 2023. She is now a senior dev advocate at Bytewax. And unsurprisingly, she's always evangelizing how to build scalable end-to-end LLM pipelines with, you guessed it, streaming data. She teaches not only concepts and code, but also jujitsu in her spare time. Fun fact, so don't mess with her. Shout out to Bytewax for partnering with us on this event. They've built a stream processing engine for Python developers that you'll get a close look at today. Now, if you've got questions along the way, we will do an official Q&A at the end. Please use the Slido link to add and upvote your favorite questions, or directly drop them into the LinkedIn live chat, and we'll do our best to get to them today. So it's time to get real with some real-time RAG. Laura, off to you.
Thank you so much, Greg, and thank you so much for having me. I'm really excited to share with you today how you can get started building real-time retrieval augmented generation pipelines. So let's jump right in. So today I want to focus our attention on 4 key areas. First, I'm going to provide an overview of what retrieval augmented generation is. Then I want to focus your attention on this idea of the data flow and directed graphs. And then we're going to combine these 2 ideas together. My hope is to persuade you that we can and we should be modeling RAG as a directed graph. And then from there, I'm going to make a switch and show you a practical application of how we can model retrieval augmented generation in real time using Python packages, Bytewax, and Haystack. So let's get started understanding what is this idea of retrieval augmented generation. It is a method in NLP that allows us to combine the power of large language models, such as GPT's models or Mistral, to extract relevant information from a knowledge base. The most popular kinds of knowledge bases these days are vector databases, and then use that information to generate content that is grounded on that knowledge base in natural language. What this essentially means is I, as a human, can go to the system and ask my question in natural language, and the system is going to go and retrieve the appropriate information from the knowledge base and give it back to me in natural language. The purpose of this is to ground the LLM in up-to-date information. What is the significance of this in the AI landscape? We've seen the explosion of generative AI in the last 2 years with the introduction of models like GPT from OpenAI. We've seen the advancement of these models into multimodal territory when we combine vision models with text models. And what RAG enables us to do is, as these models become more sophisticated and their capabilities for interpreting context become more nuanced, we can leverage RAG as a technique to enhance these capabilities by connecting them to knowledge bases. This, of course, has the advantage that, we've seen as an example for ChatGPT, they do these updates on its knowledge up to 2019, up to 2020, but time keeps going by, new events keep happening, packages keep getting updated. So at some point, it's not enough to simply fine-tune the model on the knowledge base. We have to connect the model to a database that is updated on a regular basis. Here's where RAG comes in. Some of the applications include customer support. If you'd like to incorporate an LLM as a chatbot that can interact with the user and provide more contextually relevant responses. In education, if you'd like to set up an LLM as a tutor that is connected to a knowledge base and help a student understand the content better. In healthcare, for instance, by processing patient records and by identifying or summarizing key patterns in the notes. And of course, for content creation, we've seen LLMs being used for things like marketing campaigns, creating scripts, etc. So we can apply this on a wide range of topics. Some of the benefits of RAG include accuracy. Of course, I'm grounding my knowledge base, or my LLM, sorry, in a knowledge base that I maintain on a regular basis. Relevance, of course, I am making it focused only on the content that I choose. Efficiency and scalability. So we've learned that ways to adapt the model for our purposes include fine-tuning, but these techniques, even when we incorporate efficient techniques like LoRa or parameter efficient fine-tuning, are still quite expensive because we need to curate a data set to fine-tune the LLM on, and then we need to spend resources such as GPU to actually do the fine-tuning. With RAG, we don't need to do any of that. In terms of what a sample RAG workflow looks like, so we have two main pieces within the RAG. We have the indexing piece, which is us pre-processing our data to make sure that the data goes from being a collection of text into a collection of vectors. Vectors are simply numerical representations of my text that retain semantic meaning. This is this piece right here. And then the second piece, which is the retrieval, is the piece that involves an LLM, where I, as a user, will prompt or enter my query. The query is going to be transformed into vector format. The LLM is going to be receiving the vectorized query, and the LLM that has the job of fetching the appropriate vector from the knowledge base, returning the response. We are going to then translate that response back to human language, and then we're going to return this response. Now that we have an understanding for what this idea of retrieval augmented generation is, I want to talk about this idea of data flow and directed graphs. Within the last year or so, one of the key techniques we've seen when it comes to interacting with LLMs is this idea of agents, by which we give LLMs functions or access to outside tools so they can go and perform the task that we've asked. But I want you to think a little bit in a different direction for the purpose of this webinar, and I want you to think about RAG more as a data flow and directed graph as opposed to an agentic-based solution. So I'm going to tell you what this idea of the data flow and the directed graph is. When we talk about data flow, we're talking about how data moves through a system or a process, typically through a number of different steps. If we think about Data Science 101, we learned that the classic process is we have some dirty data, and then we have to go extract it, and then we have to go and clean it, maybe perform some value imputation if there's missing values. We then want to put some modeling around it, and then we want to present the results through a visualization or a report. This very simple process can be modeled as a data flow, where my data moves from dirty, unstructured data to clean, presentable data that serves a very specific purpose. So we can think about data moving through these RAG systems in a very similar way. The role of this data flow within the context of processing pipelines, of course, is that it allows us to define the sequence dependencies of data processing tasks. Of course, we can't just go from raw, dirty data all the way to our nice report in one step. We need steps in between to get there. So we first extract, we clean, we model, we present. So we can define our sequence of steps as a pipeline. This allows us to ensure efficiency and orderly execution of tasks. Of course, I don't go from dirty data direct to model. I have to clean in between. So this order is really, really helpful in ensuring that the data is clean and manageable. The significance of processing data through this approach is, of course, we have clarity on what the transformations are and what the dependencies are. Namely, I can't model before I clean, etc. And it also facilitates optimization and troubleshooting whenever we're doing or managing the data through processing systems. Now, within the context of this data flow and processing, we can introduce this idea of directed graphs. So this idea of directed graphs comes back to mathematics, and one specific field within mathematics is the field of discrete mathematics, where we study graphs. And these graphs are simply just nodes and edges that represent the relationships between different steps. In the case of a directed graph, the edges happen to have a direction. So instead of just having a bunch of nodes with edges, the edges tell me where the information moves from one node to another. This type of model is typically used to model relationships and processes in various fields. There's lots of different applications of graph theory, but in the context of data, we're going to be focusing on this idea of directed graphs to represent how the data moves from one step to the next. Again, there's an additional property. We have the nodes and the edges. We have the path. In the case of the directed graph, if we start from node 1 and we start following our edges, we have a path in terms of, if I take node 1 all the way to node n, or the last n, the path is basically how many nodes and what order I took to get from node 1 to node n. There's another additional property within the graph, which is the cycle. And this happens when I go from node 1 to node 2 and then back to node 1. There's lots of different configurations, but ideally I'm forming a loop. This is what I mean by a cycle. And this is an interesting subtlety and difference that I want to bring your attention to. Oftentimes within the context of data processing, we don't normally think about loops. We don't normally think about, I clean my data and then I process it and then I model it and then I visualize it. And I don't really think about going back at this point. But there's something very interesting within the context of RAG. There are certain scenarios where looping is actually useful. So I'm going to share with you one package today that allows you to have this loop, and then one area where loops are applicable within the context of RAG. Again, why do we care about directed graphs and their properties? Of course, we can visualize the flow of data. In this context, we can visualize how the data moves from one step to the next. The more complicated these systems get, the better it is, or the nicer it is for me to have a visual representation of how my data changes over time. And it also facilitates the design and analysis of data processing pipelines. When I'm just thinking of a scenario, for instance, if we're thinking about a system that is fetching data from multiple sources and the data has to be processed in different ways, and the data is outputted in, let's say, a dashboard or a report or some kind of alert system, having this framework allows you to monitor, design, and observe how your system is behaving over time. Examples of directed graphs and directed acyclical graphs in data processing frameworks include Apache Spark, TensorFlow, Hadoop, Haystack, and Bytewax. Some of these you might be familiar for managing things like the flow of data, the flow of, this is particularly true for Bytewax. In the case of something like Haystack, we model the RAG problem as a directed graph. If we think of a system like Apache Spark, where we're managing different data processes, we also have this idea of directed graphs and directed acyclical graphs as one of the key building blocks. So it's not a new concept. It's an idea that has been tried and tested in quite a few domains, and in specific within the data processing domain. So it is natural for us to think about RAG and these RAG systems as directed graphs when it comes to managing the more complex architectures behind them. Again, just a little bit more on why we would want to model these problems as directed graphs or directed acyclical graphs for improving our clarity and how we can manage these processing pipelines. We can also it has an additional bonus in that we can identify where we can introduce parallelism and bottlenecks. So there may be situations, for instance, where you have lots of different entries and you want to perform the same task over and over, but the tasks aren't really dependent on each other. So instead of me going through a batch process where I just go and sequence one after the other, I can set up a parallel process where I process all entries at once using the same process. And this is the sort of mindset that I want to introduce when we work with Bytewax. Okay, so now that we had a chance to think about what RAG is, and we've had a chance to think about what data flows are, and what this idea of directed graph or directed acyclical graph is, we can now start thinking about, so it sounds like there's benefits for managing the data with data flows and directed graphs, but how do we go about modeling RAG as a directed graph? Let's jump in on this. So the key processes in RAG can be broken down very similar as how you would break down the processes in any classic data science problem. You have your data extraction, you have your data wrangling and pre-processing, and you have two additional steps that maybe we haven't seen. We have this idea of data indexing, where I'm going to take my clean data, I am going to chunk it, I am going to convert it into vector, and then I'm going to store that into a vector database. And then I have my data retrieval, where I also need some kind of mechanism to extract the appropriate vector when prompted. The last piece is response generation with an LLM. This is going to combine the retrieval piece with the large language model to ensure that not only we are retrieving the right information, but we're also generating an information that is human readable. And for those of you who may be not so familiar with this idea of indexing and why we do it, this goes back to the way large language models process information. And it goes back to this transformer architecture. I won't get a lot of time to go through this transformer architecture, but I'm going to provide you with the key ingredients about it. So the way this transformer architecture, which is the backbone of many of the LLMs that we know today, is through this idea of tokenization, where the LLM doesn't just receive a bunch of text and generates text magically out of nowhere. What's really happening is when the LLM is being given the text needs to be broken down into pieces. We refer to these pieces as tokens. And these pieces can also be further processed into numbers that retain semantic meaning. So this idea of tokenization is very important for the LLM to process information and to retrieve it. So this idea of data indexing really consists of me taking my clean data, chunking it into pieces, and then using an embedding model to transform that data from text into vector format. And when I say that these vectors retain semantic meaning, what I mean is if in the database I have the words apple, dog, and cat, if I were to represent these words as numbers in a map, I would put apple, I think I said apple, dog, and cat. Yeah, I would put the words dog and cat closer to each other than the words dog and apple. Because semantically, the meaning behind, or there's like, let's just say dog, cat, apple, and animal. Those are my fourth words. So animal, dog, and cat are closer to each other than apple is to any of those. So this is what I mean by semantic meaning. So now that I've introduced the key processes in RAG, we can sort of start seeing how I can model these processes as directed graphs, where I start from data extraction as my starting point, and I want to move that into data wrangling. That's my next node. And depending on how much data wrangling and pre-processing I have, I can either do it in that node, or I can move it to a separate node. So we start extraction, processing, and then from here, I can move on to the next node in the graph, which is indexing. Now, at this point, these three steps can typically be combined into one pipeline, depending on how complex they can be. The end result of this three steps is typically I populate a vector database. And then from here, I can combine these two into another pipeline where I can connect to my vector database. And when the user prompts the LLM, or it asks it a question, this specific pipeline can then combine the power of generative AI with the retrieval mechanism to return a human readable response that is relevant based on the user query. Okay, so now that I had a chance to introduce that, I want to talk a little bit about how we can build these kinds of systems using Python with two of my favorite frameworks. One of these is Bytewax and the other one is Haystack. So for those of you who have been watching my journey at the AI Makerspace community, you know I've been a big lover of the Haystack package for a long time. And I've been very excited to combine Haystack with Bytewax and build real-time RAG pipelines. I think it's been on my radar for a while, so I'm very excited to show today to you how I was able to combine these two frameworks to set up one of these extraction, cleaning, and indexing pipelines and perform the updates in real time with the Bytewax framework. I'm going to tell you a little bit about what each of these frameworks does. So Haystack is an open source framework that is built with Python that allows you to build scalable search systems with a focus on retrieval augmented generation. Haystack was founded in 2019, and back when they started, was it 2019, 2016? I think it was a little earlier than that. They had a big focus on NLP, and they back in the day before LLMs exploded, they would work with language models. And so they had set up a lot of mechanism and tools for building search system using models like BERT, where we would do classic NLP tasks to perform searches. And they supported the farm package if you wanted to fine tune some of these models. And then later on, they evolved into Haystack, which is more about leveraging models from Hugging Face to perform search over a collection of documents. Now, when LLMs were introduced in 2000, what was it, 20? I think it was, I don't know, 2021, 2022. I don't have a good sense for dates, but when LLMs were introduced, a lot of things shifted. Suddenly, we had the ability to generate text in a much more contextual way. We had a way to call these LLMs in a way that was much easier. We had the introduction of pinging an LLM or making inferences from an LLM through an API. And then from this, another explosion happened. We also had an explosion in embedding models. We had an explosion in vector databases. We had an explosion in agentic frameworks. There were all these different tools out there doing all these tasks. And so the team at Haystack decided, okay, we're going to revamp our current functionality, and we're going to go ahead and make it much more adaptable and ready to work with the new tools and new models. And so they spent last year a good chunk of time redesigning Haystack into what is now known as Haystack 2.0. So that is what I'm going to be showing you today, how we can build that 2.0 pipeline and combine it with Bytewax. Now, on the Bytewax side, our Bytewax is a package that uses the Rust package timely to set up tools for stream processing. So the way it's built is we're using the Rust package timely, and we have a Python API on top of it that developers can use for building real-time data processing applications. The goal of Bytewax is to support stateful processing and real-time data flows. So when I talk about stateful processing in the context of streaming analytics, think about the flow of data as a river. I think that's an easy way to think about it. And if I think about a river of data, and a river of data that's changing in real time, you know, some of this data might change. Maybe there's a signal coming in, or maybe there's a specific process that I need to apply to the stream of data as it comes in. And so some areas of the stream, I don't care about the state as much. Some areas of the stream I can just pass, but some areas I really care about the state. I really care whether the data has been cleaned or not. I really, specifically in the context of fraud detection or anomaly detection, I really care about what the state of the data is. I really want to know whether it satisfies a specific property. I want to have the ability to do things like windowing, and I want to have the ability to manage workers in a different set. So what Bytewax allows you to do is allows you to connect your favorite Python packages with this concept of streaming and processing. So we give you the tools to build with the packages that you love. And I think the trickiest bit about moving from something like batch processing, which was something that I think it was part of my core development as a data scientist. The shift from moving to batch processing into stream processing is stop thinking about processing your data using for loops and start thinking about processing a single entry in your data and then applying that process to all of the other entries, either through async programming or through some of these functionalities that we provide, like state management, windowing. So that shift took me a little bit of time to make. But once I got it, I found that this specific approach allows you to really zoom in and think about, how do I want this single data point to be transformed? And then how can I apply this to the rest of my data set in a way that is efficient and flows from one step to the next? So we're going to be working or playing with this idea of data flows in a bit. For Haystack, we can install it with pip as pip install Haystack AI. The building blocks for Haystack are data structures, document stores, components, and pipelines. In terms of the Haystack data structures, so we have the document, the byte stream object, and the tabular data document. So this is just ways for me to transform the data from raw format. So it's a web page, or it's a PDF, or it's a, I don't know, even an Excel sheet. And my goal is to transform that from whatever it is into a document object. These document objects, if you've worked with LangChain, are very similar to that kind of document object, where I will have an ID, I will have the content, and I will have some kind of metadata. And we have additional data structures to support streaming events. This includes a streaming chunk, where I can process image and audio, and LLM chat messages. The last kind of data structure I have includes data structures for Q&A systems, answer data structure, extracted answer, and generated answer. So all of these data structures, you don't typically tend to see them when you build these pipelines, but it's usually what's flowing in between the different steps. So this, when I learned about these data structures, and when I learned about the philosophy behind Bytewax, I knew I wanted to explore the connection between the two. Because I saw, okay, so Haystack has set up a really nice set of data structures for me to manipulate my data, and they have this compatibility with streaming data sources, and they're also very much building with this idea of putting together components into pipelines. So when I understood that Bytewax philosophy or way of thinking is through this concept of the data flow and the directed graphs, I knew I wanted to put them together and see what I could build. So from here, what I want to share before I can show you what one of these pipelines look like is I want to show you a bit more about these what the building blocks of Haystack are. So remember, we have the data structures, we have the components, and we have the pipelines. Haystack offers key component categories for each of the different steps in the RAG workflow. We have components for data pre-processing and wrangling. We have components for embedding. These embedding components really just allow me to connect to different embedding model providers like OpenAI or Hugging Face, Azure embeddings, Amazon embeddings, etc. So any embedding provider you can think of out there, the component just allows you to make a connection to those providers. We have connections or components for writing the embedded content onto a vector database. And again, there's the additional tool that we have is this idea of document stores, where the document stores are just integrations, or they're just these, they're not a component, but they're basically an object that allows me to write my vectors onto a document store that is both compatible with the Haystack framework and the vector database provider. And then for the retrieval piece, we have components for retrieving, for ranking. We have components for the LLM generation piece. Again, it's very similar to the embedding component. It's just a component that allows me to connect to different providers. And we have routing. Additionally, and the pipeline that I'm going to show you today, they also have this framework for building custom components. And the modality for building custom components is, I think, the most powerful feature of Haystack 2.0. And it's what allowed me to make the mix between Bytewax and Haystack so seamless. Through the custom component, all I have to do is define a class with a run method using their component decorator. And my definition, in my run method signature definition, I also want to add the kind of data structure. So again, this goes back to thinking, are we dealing with document objects? Are we dealing with streaming objects? Are we dealing with Q&A objects, or those kinds of data structures? And then from there, I can just use Python in any way I want to perform my data processing. One thing that I think absolutely blew my mind is that you can wrap pipelines as custom components. And I use this technique for my data flow. I'll get to show this in the code at the end. But essentially what I did is I defined a custom component that whose definition consists of a Haystack pipeline. And it might take a little bit of time to wrap your head around it, but the end result is that I can run a single pipeline as a step in my data flow, which absolutely blew my mind. I'll do a demo of this at the end, and you'll see. I want to show you, before I go into the code, I want to stop sharing this and share for a little bit what sample directed graphs from these Haystack pipelines look like. So in here, let's just do the simplest one I can think of. Okay, so here's a Haystack directed graph of me extracting information with a search, the SERP dev web search component. So this is just going to take a question in natural language, and then it's going to use the SERP API key to retrieve information from the internet. From here, I'm going to have a bunch of links, and then I'm going to connect this to another component that takes as input a link, and as output, it returns a stream of HTML objects. So here's just a simple, what these Haystack directed graphs look like. Typically, I return a list of document objects, so I don't want to have just a bunch of raw HTML. What I actually want is the content of the web page. So this specific data flow, or this specific directed graph, extracts the content from the web using a natural language query. It extracts the content of each of the web pages using the link content fetcher, and then it stores the content of those documents into a document object. So this is what an extraction pipeline would look like. If I want to do something like indexing, the indexing has a bit more steps. So this specific data flow assumes that my sources are a bunch of markdown documents. So in this case, I can use a component known as the markdown to document, which is just going to convert markdown into document object. And then from here, I can perform cleaning with the document cleaning object component. I can split it. Remember, we don't want to give a big paragraph of text to the LLM. We want to give it chunks to it. So we split it. We can then embed it, and then we can write it into our document store. So this is a directed graph for what an indexing pipeline looks like. If I wanted to share what, let's just take a look at this one. So if I wanted to show something like loops, and pardon that the background is a little ugly. So this is an example of a Haystack directed graph where there are loops in this. So in here, this specific one is more on the retrieval piece, where this specific pipeline is using the LLM to autocorrect its responses until it returns the right response. So in this case, I have a prompt builder as my starting component, and I just have the instruction and whatever information I want to give it. I'm going to give that prompt to the LLM component. And then from here, I'm going to have another component called the output validator, where once the LLM generates a response, I don't want to just give that to the user. I want to validate my response. Oh, Sarah, can I have the screen back on? Oh, let's just go back, share screen, window, share. Okay, thank you. Okay, so where was I? Okay, so I'm going to start from the beginning since we lost the screen. So in this specific pipeline, I start with the prompt builder. This is just a component that takes as input the instruction that the LLM is going to receive. This is then fed to the LLM. And then, as I mentioned, this specific loop has the purpose of auto-correcting the result until the output validator says it's correct. So in this case, the LLM is going to generate the response. We're going to, if it fails, we're going to give that back to the prompt builder so that it can fine-tune its own response or auto-correct its own response. And we keep doing this loop until output validator passes. Once this output validator passes, we can then return the response. So this is one specific use case where we might see the use of these loops, where DAG is actually getting in the way and we want to be able to go back. So I'll stop the share and I'll go back to the presentation. Window. Let's just do Chrome tab. Okay. So this is what some of the directed graphs of Haystack pipelines look like. So we saw one sample for extraction, we saw one example for indexing, and we saw one example of a loop for a prompt builder with an LLM and a mechanism to fine-tune or improve the LLM's response until the output validator says it passes. Now that we know what the building blocks for Haystack are, and now that we know what these RAG systems, or what these RAG directed graphs look like, I want to go back to focusing my attention now on how Bytewax works and what are the key concepts behind it. So as I mentioned before, Bytewax is a Python package that allows you to build stream processing with your favorite Python tools. Some of the key concepts for Bytewax include this idea of workers in parallelization, whereas we can think of the data when we're managing the data in a streaming as processes, and so we have this idea of data flow programming, which again, by this I mean we have the data moving from one step onto the next. We have this idea of joining streams. This is particularly useful, for instance, when you have two streams of data that you can join, say, by an ID. This idea of joining streams is, you can think of it very similar as you would join two SQL tables. You might have one stream with the ID field, and another stream with the ID field, and you want to bring these two streams together. We also have this idea of windowing, and windowing can come in particularly handy, for instance, when you want to do something like anomaly detection, or when you want to do analysis on, let's say, financial data or data with a time series component. Let's say that you wanted to do something like a rolling average, the purpose of streaming, of course, is that as new data comes in, you continue to process the data in real time. So if I were to describe, for instance, the batch version of classic ML, I extract my data, I clean my data, I apply some scikit-learn model, and then I have my model that I can use to make predictions on the new data. Streaming is a little bit different because the data is constantly changing, and so we want to update the model in real time. We want to make sure that the model is informed and has access to the latest data. So with something like windowing, we can sort of take a look at a specific subset of the data, or even a specific window of the data, and then shift our model so that it's adjusting appropriately. We have a little bit more advanced concepts around the idea of connectors and operators, but the two ones that I'm going to be focusing on today for this workshop is this idea of the data flow and this idea of operators, where the building blocks for my Bytewax data flows are, I'm going to start a data flow. I'm going to then feed steps onto the data flow, for example, my input. And then with the operators, what I can do is I can map the operations onto the data. So one of the classic applications of this, if I think about, let's just talk about data science 101, where I think about data extraction and cleaning. Extraction, I can either read from a file, I can connect to a Kafka instance, I can read from the internet. From there, I would want to deserialize my data so that I'm only dealing with one entry at a time. And then I might have these functions that make changes on the data. So maybe I have a function that extracts, or I have a function that cleans, or I have a function that models. So within Bytewax, what we do is we use the operators to map these functions onto the data. And so in the way the data flow looks like is I have my input, I deserialize, and then I apply my functions through the map operators. We have both stateful maps and stateless maps, which we can get into depending on whether we want to manage memory or if we want to track changes on how the data changes over time. In terms of what this idea of workers is, so the workers are simply distributed components that allow us to process the data in parallel. Of course, what this allows us to do is it gives us scalable and efficient handling of data streams. We don't have to be stuck on one process and wait for that to finish. We can simply set our workers to work in parallel. And one of the key assumptions for us is that we use this idea of identical workers, and the workers execute all steps, including input and output in the data flow. The other topic or the other concept is this idea of state management, which allows us to maintain across streaming events. Event is also one critical component. Event is basically what the stream is receiving as the data moves from one step onto the next. And again, this idea of stream processing is it allows us to change or manipulate the data as it arrives, as it changes, not in a batch, like I'm going to do this once a day. No. This second, if the data changes this second, then this second I apply the operation. This is really suitable for real-time applications where low latency is very important. Now, this is a part that I'm very excited about. So when I started to learn about Bytewax and the philosophy behind it and the building blocks behind it, I remembered Haystack's approach, and I remembered the way Haystack manages the data structures. And so we can sort of think, when we combine Bytewax and Haystack, Haystack gives us the pipelines, Bytewax enables the data flow. So I'm super excited to share with you this next piece. I'm going to share with you a code snippet for what these two things look like together with an indexing pipeline. So in this case, my application is an extraction and indexing pipeline. My goal is I'm going to be reading from web pages. My input is a JSON-L object that contains URLs. I want to build a pipeline that extracts the content of those URLs, cleans it, chunks it, and embeds in real time. So if you're wondering, oh my God, all these concepts, the workers, the state management, the parallelism, I don't even know where to start. Don't worry. This is legitimately what a real-time DAG data flow looks like for this specific use case. I initialize my data flow, rec pipeline. I initialize my input. In this case, op input is my operators. So I'm going to read from a file called test.jsonl. We can change this file source to be a Kafka instance if you want to read that in real time, or a Red Panda instance. From here, we have a function that deserializes this JSON-L object so that I'm only reading one of the entries. And then this step right here, this is a Haystack pipeline, okay? So I built an extraction and indexing pipeline, and I can run it as a single operation. So I'm gonna go ahead and stop this. I'm gonna share what this looks like in the code. Share screen. Okay. So here is what my pipeline looks like. So all of these are just Haystack imports. I've built a serialize function. All this is doing is just reading my data. My data consists of these JSON objects that contain URLs. And then all it's doing is just reading that. And then here's my custom component. So within Haystack, the way we define a custom component is as a class with a run method, okay? Now, what absolutely blew my mind is that I can define a Haystack pipeline as a custom component, which means I can initialize my components in here. I extract, I use the link content fetcher to get the web page. I transform that into a document object. I clean my document. I split my document. I apply an embedding model. I connect my different components into a pipeline. And then in my specific case, the reason I defined this way is because I wanted to attach additional metadata. So this specific object has an ID and a headline, and it also has a ticker symbol. So this was news from the stock market. So I wanted to save additional metadata. So I just built a custom function that appends that additional metadata to my document object. So in here, I run my pipeline, and I just add my additional metadata, and I just have an additional method to convert to a dictionary. So all I have to do to run this in real time, this is a Haystack pipeline. All I have to do to run this in real time, in this case, I'm not assuming any state management, is I initialize my custom component. I have this function here called process event. And this process event is going to be listening. When I talk about events, I just mean the instances of data moving through the different steps. So it listens to this event. I'm going to go ahead and read the event. So in this case, it's going to take one of my entries from the deserialized data, and then it's just going to apply the pipeline. And now the fun part. So here's what I have to do to run my data flow. And what we're going to see is we're going to see a stream of embedded documents. Okay, it takes a little bit of time to do the imports, but once it gets running, what we're going to see is a stream of all of my data entries being processed. And of course, this has to happen the day I'm doing a demo. There it is. Okay, so what we're seeing here is a stream of documents. So in here, what's going on is Bytewax is running in real-time extraction of all of these URLs in here. It's extracting the content of that document, is performing the cleaning, the chunking, and then it's applying an embedding model to calculate the embeddings. So In this tiny piece of code right here, I've gone from reading the content of this JSON object, deserializing it, and applying a Haystack pipeline as a single mapping, which is absolutely mind-blowing to me. What would be next from here is to write these embeddings onto a document store that supports streaming. And for this, I'm going to go ahead and stop sharing this and share with you another very cool insight that I want to share. So in here, what I have is a little bit more of an advanced architecture for where we go, where we want to go with this. So right now, of course, I'm not, the data that I did the demo on is not data that is changing in real time. That is just a static JSON file. But in order for me to set up a real-time data stream, what I would want to do is I would want to set up a Kafka instance, and I would want to build a Bytewax pipeline that is extracting the URLs from different sources. It's populating the Kafka instance with those topics. I go and deploy that Kafka instance on Azure. And then from here, I can set up my real-time indexing pipeline so that instead of reading my JSON file, it's listening to Kafka. From here, I'm going to go ahead and do data wrangling. I can use different models. For this specific one that I'm showing you, I'm using productionized LLMs. So I'm going to be using models from Azure. I'm going to be leveraging some functionality from unstructured, and I'm going to orchestrate the whole thing with Haystack. I feed that into a vector database. This specific solution assumes that I'm working with Azure's Search AI. And then from here, I can set up another 2 pipelines. This one in here is an alert pipeline that is listening to Kafka for whenever there's a new set of news coming in. And it's enhancing the content of the vector LLM by not only extracting the relevant information that is already there, but also listening to any new topics that come in. And this specific retrieval pipeline in this architecture is only triggered when a user comes in and asks a question. So maybe the user wants to know, hey, can you tell me any relevant news for Microsoft, Apple, and Google stock? The LLM goes and fetches the information from the vector database and any relevant information from the Kafka topics, generates a response, and then returns the report in human language. Now, we won't have time to go through this today, of course, but this is a really nice segue into the next workshop we're teaching, which we're going to show you how you can implement that specific architecture along with Microsoft and unstructured. So if you are curious to learn more about setting up these processes so that instead of reading from a static file, we're actually listening to data that is changing in real time through something like Kafka or Red Panda, our next event is going to take place on June 4th at 10 a.m. I'll drop the link on the chat for you. And in this event, what we're going to be focusing on is specifically how we can set up this architecture and how we can implement this architecture for a production-ready, real-time RAG system. So we do hope to see you on June 4th for this event, where I'll have a chance to go a little bit more in depth on how we can set up these pipelines, how we can set up these processes, and how we can deploy these services for a system that is listening to changes in real time. So just final thoughts, since it was quite a bit of information, but some of the final thoughts that I want you to leave with today. So today I had a chance to explore 2 key topics with you today. This idea of the data flow, which is the process or the philosophy of taking data and moving it from one step onto the next. We saw this idea of directed graphs, where we can represent the steps as nodes and represent the movement of the data from one node to the next with a directed edge. And then the other concept we saw was this concept of retrieval augmented generation, whereas what I'm doing is I am enhancing the capabilities of an LLM by connecting it to a knowledge base and setting up processes to allow the LLM to retrieve relevant information. The last piece we saw is how we can combine the 2 ideas, whereas what we're doing is we're identifying the key steps in the RAG workflow, and we're modeling each of those steps as directed graphs. The last thing I shared was how we can bring Haystack and Bytewax together to basically go from this idea of modeling to real life. Whereas what I'm doing is I define a Haystack pipeline. I can run the pipeline in batch. But if I wanted to run it through something like Bytewax through a data flow, then the two concepts that I used in this specific workflow were the idea of the data flow and this idea of mapping steps, whereas I define each function as one of my steps being a data pipeline. I execute the steps in the specific order, and I wrap this into data flow and operators. So I think with this, we can open up the room for questions, Greg. So if I could have Greg back in the room, and we can take questions from the channel.
Yeah, great stuff, Laura. So you took us through a lot today. And one of the things we can kick off kind of the Q&A, we got some great questions in the chat. Keep them coming, guys. One of the things that struck me is you said, well, we really need to stop thinking about processing our data through for loops when we go from sort of a batch processing thing to a stream processing thing. And you said, start thinking about it as sort of processing your data one piece at a time. And then you talked about sort of using async, and you were talking about kind of doing transformation on one piece of data at a time. Can we just start off the Q&A by kind of slowing that down a little bit?
Yes.
and talking a little bit more about kind of the way to think through that particular concept? I thought that was really great.
Yeah, of course. So this is where this idea of identifying the key steps in the pipeline become really crucial. Because, and I guess when I hear for loops, there's two ways to do a for loop. One way is where you have your directed graph, you have identified the steps, and you're just applying the steps iteratively. There's one for loop approach. The other for loop approach is a terrifying for loop approach, where you're doing everything inside the for loop, and it's very difficult to separate what's going on. I find that for loop very scary because it's usually for, and then there's like a huge thing of things. So I think moving from this for loop approach to a single approach, I would say identify what are the key steps that are happening. Again, if we think about classic data 101, extraction, cleaning, modeling, presenting. Those are the 4 steps, okay? So if we think about how is one single data point transformed into one of these steps, we can, that is the framework. Now, in terms of that's the first stage, from going from this scary for loop to this more manageable for loop. Now, to remove the for loop altogether, once you identify the key steps, we now think about events. We think about, okay, so if I were to take just a single data point and I were to think about how is this data point going to be transformed, then I break down my steps or functions in such a way that they're independent from each other. So it's like I take my raw data, I pass it through the next step, and I should have a data structure that I know what it looks like. It's clean. So that new data structure is then what is fed to the next step. So there's an independence in between the different nodes and an independence in between the different components.
Nice. Okay, so yeah, just getting really systematic then about exactly what each and every step is that each and every data point goes through. It's sort of, you have to get more granular before you can actually set up kind of pipeline systems that are working in real time. I've got a technical question. This one's from Manny. This one, he says, how would or can I use this sort of approach if I had a relational database management system with databases and a table, or if I had a NoSQL database and I wanted to sort of export the data into Haystack? Can I just then use the vector DB to make RAG apps? Is this pretty straightforward to go from kind of the structured data or the unstructured data into Haystack and build RAG? And have you had any other sort of events that you could point Manny to?
Yeah, absolutely. So going back to how Haystack models things, so we have the components, we have the pipelines, we have the data structures, and we have the document stores. And the document stores you can simply think of them as Python APIs that allow you to connect to different kinds of database flavors. The NoSQL database flavor that they support is Elasticsearch. I don't recall if they have recently released a MongoDB document store as well. But what I'd recommend is that you go, I'll just put a link on the chat. Documentation. So I'll just link you here. If you visit the URL that I've shared, and I hope it's shared on the chat as well. Maybe I'll share my screen.
Yeah, we'll make sure it gets shared.
Okay, so in there, what you can see is a list of document stores, and they support all the way from in-memory to a bunch of different vector store providers. Oh, and they do support, so for NoSQL, they support both Elasticsearch and MongoDB. So what I'd recommend is on the URL that has been shared, you can also navigate through the tutorials and see how you can get started setting up one of these pipelines. Okay. And then from there, just plug in which document store provider fits your needs, whether it's Elasticsearch or MongoDB. If to your system you're also adding VectorDB, I think what's important to determine in that case is, does it make sense to have both a NoSQL and vector database? Or do you want to migrate from NoSQL to vector? What is in the NoSQL database that can be vectorized? Because maybe you have a combination of unstructured and structured. So I think that's important to determine as well.
Okay, very cool. So we've got a couple more that we want to try to get through here in the next few minutes. How would you compare Bytewax with JobLib? Is this an apt comparison? How would you compare?
Oh, that is a good question. I have not had a chance to work with JobLib before. What I can say about Bytewax is our focus is to let developers build with the Python packages that they love. That is our angle. So if your workflow involves building Python pipelines, either for RAG or any other kind of process you want, and you really want to, you're really struggling to, some of the challenge sometimes with streaming is you sort of have to make the jump from Python to the other language. So what we give you is that capability, continue building in Python, and we just give you the streaming capabilities out of the box.
Okay, cool. And Manny's definitely in the Discord, so if you want to follow up with him on JobLib stuff, at the Neo Matrix 369. What up, Manny? Next up, we've got, how would the joins work if the data streams are not synchronized? Is there like a time window when like a join can happen?
Yeah, so the joining, we can do the join through a common field. So even if the joins are not synchronized, when you say, oh, maybe synchronized is interesting. I think by synchronized they mean we have a stream that was updated sooner than the other, which is, I think, if I understand the question correctly. I mean, I would ask why that's happening, why the streams are not synchronized.
Oh, interesting.
Yes, but in terms of getting streams that have incomplete information and joining them, the way we would do it is through a common field or an ID. The way you would do a join in SQL, you use a common field between two tables. The difference is you use a field between two streams, and then you can bring them together.
Okay.
But yeah, we would assume
better
both
to
streams
synchronize them before the join.
Yes. Yeah. But I don't know what synchronized means in this case. I mean, you could have streams from different time periods, but if there's a common field to join them, you can join them.
Ooh, okay. Yeah. Like the timestamps don't have to be, and they often are going to not be exactly the same in different places. Okay. Yeah. So, feel free to kind of follow up with Laura either in the Discord or at her contact info on that comment and question. And then sort of, last one here. Which advanced RAG techniques does Haystack use? Are there more of, or like, let's just go with that. Which advanced RAG techniques does sort of Haystack use? We sort of think about maybe improving our RAG system from something that's a bit more basic.
Yes. So they support keyword-based, retrieval-based, hybrid. If you check, I don't remember all of them to the top of my head, but if you go take a look at the retriever documentation, there's a bunch of different techniques that they support. Yeah, so they have sparse keyword-based, dense embedding-based, sparse embedding-based, filter retriever, and then for the advanced one, what they do is they combine, you can combine the different retrievers. They have multi-embedding retrieval as well. So I'll just share a link here for the different kinds of embedding retriever techniques that they support.
Awesome. Awesome. And then the last question, I'll go ahead and take this one, Laura. Why is Laura called the legend? Well, everybody, our ethos here at AI Makerspace is to build, ship, and share. And when you can do that, we like to call it doing that like a legend. And it really does align with our community values of kind of building, shipping, and sharing at the LLM edge. It aligns with giving through teaching, and it aligns with, as you've noticed here today in the Q&A, really embracing I don't know and figuring out what you need to learn next. So as you've seen today, Laura really embodies all of these community values of ours, and she was one of the earliest folks in the game to be doing concepts and code by herself. So shout out to Laura. Thank you so much for joining us today, Laura.
Thank you for having me, Greg. I love being part of the AI Makerspace community.
Awesome. Thank you so much. It's time to wrap up, everybody. Okay, so final couple of things. If you enjoyed this sesh, Laura's got another one next week. She's talking about unstructured in Azure. Check it out. Keep supporting her journey. And you can also find her, of course, in the Discord. So if you're not in there, go ahead and get in Discord right now. Start building, shipping, and sharing your way to the edge like a ledge. And if you're ready to accelerate your Gen AI application development out to the edge, join me, the Wiz, the best peer supporters around, and fellow aspiring AI engineers and AI engineering leaders to teach and learn with. We kick off cohort 3 of the AI Engineering Bootcamp next Tuesday. There's still some slots left, May 28th. Certified AI engineers will get free access to hiring partners, career coaching, and really white glove support from me personally and our small team to help you get to the next level you're trying to achieve. And as always, until next time, keep building, shipping, and sharing, and we, along with Laura, will most certainly do the same. Thanks, everybody. Have a great rest of your week. We'll see you soon.